Hello everyone, this is the second video of the Transformers architecture where we will dive into the math. The previous video we saw the theoretical part, and now we're going to delve into the math. So we're stripping away the abstraction to look at the raw numbers. We're going to trace exactly how a computer turns the input. For example, let's go into prediction using the matrix multiplication, linear algebra, and the probabilities. We will see how we take words, turn them into vectors, and perform the calculation of the attention. So, first, let's define our matrix dimensions. N is our sequence length. In our example, let's go, or I am 2. D model is the size of the vector representing a single word. For example, in the original paper, it was 512. V is the vocab. It is the total number of words we know. For example, 3000 words plus. To start, we represent our input not as word, but as one hot vector. So 1 and the others are 0. For in the let's go, we create a vector with zeros around a single 1 at the index for let's. We do the same for go. This gives our initial input structure. So for the first step, input embedding, we convert our one hot vector into dense vectors that capture meaning. Mathematically, we multiply the one hot vector, which is the size of 1 by the v, by a learned embedding matrix, weight matrix, of the size v times the d model. So if the input for let's is 1, we multiply it by the weights to select a specific row. For let's, we might get a vector like this one. For go, we get the different numbers. We stack these to form our input matrix, which has a dimension of n by the model. So in our case, 2 multiplied by 512. So the second step, which is the positional encoding, since the model processes let's and go in parallel, it loses the order, so we must mathematically inject position. We use, for example, the specific formula involving sines and cosines of different frequencies. So for the word let's at position 0, we generate a vector using these sine waves. For go at position 1, we generate a vector using the cosine waves. We simply add these numerical values to our embedding matrix. So x final is the x of embedding plus x of position. So crucially, this addition does not change the matrix shape because we're doing addition. It remains 2 multiplied by 512. So now we reach the core math. Creating the queries, keys, and values. So we do not use x directly. We train 3 linear layers, which are just weight matrices, W, Q, K, and V. And we perform matrix multiplication. So Q is the x multiplied by V. WQ, K is x multiplied by WK and WV. So if our input x is 2 by 512 and our weight matrices are 512 multiplied by 64, the resulting Q, K, V are compressed into 2 by 64. Row 1 of Q is represents the query for let's. Row 2 represents the query go for let's go. Now for the third step, we calculate the dot product to find similarity. We want to know how much let's relates to go. We calculate the dot product of the query matrix Q and the transpose of the key matrix K. So the score is Q multiplied by K transposed. So the score is Q multiplied by KT. So the math is 2 multiplied by 64 multiplied by 64 multiplied by 2. We get a 2 by 2 score matrix. So now for the fourth step, we do scaling and softmax. First, we divide our scores by the square root of dk, just so we can remember this part is this part. Okay. In the paper, the original paper, dk was 64. Here we're using an example of 8. So no, 64, the square root is 8. So we divide by 8. This keeps the gradients stable so they don't explode. Next, we apply the softmax function. This squishes our row scores into probabilities that sums to 1. So minus infinity is 0, plus infinity is 1, and all the values should be between 0 and 1, and their sum is 1. So now this is the weighted sum step. We take our probability matrix 2 by 2 and multiply it by our value matrix 2 by 64. So okay, probability Z is probabilities multiplied by the V, or the value matrix. Since so after that we get the conceptual output, contextualized output. This output is our context-aware embedding for this specific attention head. So now we are here, this part. We did this, scaled by dividing, and then apply the softmax function, and now we are here. Okay. This was just one attention head. In the original paper, they used multi-head attention with 8 heads, so H is 8. We performed the previous calculation 8 times in parallel with different weight matrices. So we have W, Q for the queries 1, 2, 3, 4, 5, 6 until we go to 8. This gives us 8 different Z matrices. Each one has the size of 2 multiplied by 64. We concatenate them side by side. Finally, we multiply this big matrix by an output weight matrix WO to blend the information. The result, we are back to our original size 2 multiplied by 512. Okay, once we do that, we do the add and norm. We add the residual connection. We take the original input X we started with and added to the output of the attention block. So x plus z. This creates a highway for gradients during backpropagation, making training deep networks possible. And then layer normalization. We compute the mean and variance for every single word vector and normalize it. This ensures that the number stays within a stable range. Okay, so now the next step is we use the position-wise feed-forward network. This is a sample neural network applied to each word independently. It consists of two linear transformations with the ReLU activation function in between. So the formula is the max 0 between 0 and x w1 plus the bias weights and bias. This is the input multiplied by the weights plus the bias, second ones. We project our vector size up from 512 to 2048. Apply the ReLU, so we turn the negative values to 0 and project it back down to 512. This allows the model to learn complex nonlinear relationships. Okay, now we move to the decoder. During training, we use masked self-attention because we need to ensure we do not see future words or tokens. So to do that mathematically inside the attention score matrix, we set the values at the upper triangle, so this part, to minus infinity. So when we apply the softmax, minus infinity becomes 0. So this is the upper triangle, becomes 0. This forces the attention probability for future words to be exactly 0, ensuring the model is autoregressive. So the bridge between the input and the output is the encoder decoder attention. Here the math changes slightly. The query Q comes from the decoder. The key and value, so K and V, come from the encoder. We calculate the dot product. This allows the word to mathematically find and focus the let's say if we're going to be using an Spanish to English task, this allows the Spanish word to find and focus on the English vector for the corresponding word. Finally, we need the word, so we take the decoder output vector 1 with these dimensions, 1 by 512, and we pass it through the linear layer. This multiplies the vector by the vocabulary matrix. This result is a vector of 3000 scores or logits. We apply the softmax one time to get the probabilities. Then we can select the token or word with the highest probability if we're going to use the greedy search, or for the beam search we will take the other tokens with lower probabilities into consideration for generating the next word. So to wrap up the math, we turned the words into vectors. We projected them into the queries, keys, values, spaces. We calculated the similarity using the dot product. We normalized with the softmax. We calculated the weighted sum of values. We projected back the vocabulary size to predict the next token. So in the next presentation, which is the final one regarding the transformers, I will try to open up a code editor and write these exact equations in Python, so I can practice better this concept. So thank you for watching. Please like and subscribe.